Alright, so here's an example of axial stress. So we're supposed to find the normal stress in rod 1, that's this two-force member BD for the mechanism shown in figure 1.8. What we are given to do that, we're given that the diameter of that rod is 8 millimeters. We need to know that because stress is force over area. So we'll use that diameter to calculate the area. We know that load P is 2,300 newtons. This is 2,300 newtons. It acts in both of these directions. And then we're given the dimensions that A is 120 millimeters, B is 200 millimeters, C is 170 millimeters, and D is 90 millimeters. Okay, and then, like I said, we're going to find the normal stress, that's sigma in bar 1. Okay, so if we look at this whole system, we have 2 pins. We have a pin at C, so we have 2 reactions. It's a CX and a CY, and we have a pin at D. So we have a dy and a dx. So we have 4 unknowns and only 3 equilibrium equations. So what we're going to do is break this system apart, and we're going to start by looking at just the wheel. And the reason why is because at A, there are internal reactions in the X and Y direction holding the wheel onto this triangle. So if we look just at the wheel, we'll have a circle, and we'll have this P force coming out at 60 degrees, and P equals 2,300 newtons. And then we have a P force coming out horizontally, which is also 2,300 newtons. And then what we have is right in the center at that pin, we have a reaction in the X direction, AX, and a reaction in the Y direction, AY. Why this helps is when we look at the triangle next, those same AX and AY will have the same magnitude, but they'll be in the opposite direction. So we'll start by solving for AX and AY, and we'll do that with statics. So just our equilibrium equations of sum of the forces in the X equals 0. So that equals AX minus this 2,300 Newton P force, so minus 2,300 newtons, minus the X component of this P force. So the X component of that is going to be 2,300 newtons times the cosine, the adjacent of 60 degrees. And then if we solve for AX, it's our only unknown in the equation, we get AX equals 3,450 newtons. So then to solve for AY, we do the same thing, only we sum forces in the y direction. Those add up to 0. I have AY drawn positive as well. I forgot to put my little axis label here. Y is positive up, X is positive to the right. And we have AY is positive. We don't have to worry about the horizontal P force, but we have to put in the Y component of this P force at an angle. So that is in the negative Y direction, and it'll be 2,300 newtons times the sine of 60 degrees. And we're going to get that AY equals 1,991.86 newtons. All right, so we're going to take those, and now we are going to look at just this triangle. So when we do that, look at the triangle frame. So we're going to draw another free body diagram. And looking at our picture, this is A, this is B, and this is C down here. Go draw, draw A over here. So, like I was saying, A is the reactions at A on the triangle are equal and opposite to what we just calculated. So that means AX is going to go in the negative X direction, and AY is going to go in the negative Y direction. So this is AX, and we found out that that is 3,450 newtons, and AY is 1,991.86 newtons. Okay, so then at C we have, it's a pin, so we have CY and we have CX, and I usually just draw them positive. And then, so that's this pin that we drew the reactions for at the beginning. And then at B here, we just have that internal force along bar 1. So at B, we have F1. Alright, so now we know the reactions at A, we don't know the reactions at C, but all we really care about is F1. So if we take a moment about C, L equals 0, then we don't have to worry about the reactions at C, and we can solve for F. But we need to draw some dimensions on our diagram first. So the distance between A and B is 120 millimeters in the horizontal direction. The distance between A and B in the vertical direction is 90 millimeters. and the distance between A and C is 170 millimeters. So we definitely need dimensions when we're taking moments because it's a force times the distance. So we also need to calculate what this angle theta is. So if we look up here, theta's here. The opposite dimension would be this distance between C and D. So if we did tangent, we would have opposite, which is 200, over adjacent, which is this combination adding D plus C. So before we sum the moments, we're going to calculate theta. And that is tangent of theta equals the opposite distance of 200 millimeters all over the distance adjacent to that angle, which is 90 millimeters plus 170 millimeters. And we get that theta equals 37.57 degrees. So then we can sum the moments about C. And that's going to equal AY. So this AY force is pushing down around C, and if you use the right hand rule, your thumb is going to point out of the page, so it's going to be a positive moment. So it's going to be a positive 1,991.86 newtons times the perpendicular distance between A and C. So the distance between A and C here is 120 millimeters. So times 120 millimeters. Okay. So then if we look at AX, that is also going to be a positive moment. So it's going to spin it around C in the positive X direction, or in the positive Z direction out of the page. So we would have plus AX equals 3,450 newtons times the perpendicular distance in between those two forces is this 170 millimeters here. So we have times 170 millimeters, and then F breaks up into two components. We would have a Y component that goes through C, so we don't have to worry about that, and then an X component, and that's the part that we'll need to calculate. So that will be the sine of theta. So we'll take, and that force is going to spin around C, and it's going to be a negative moment. So we have minus F1 times the sine of theta, which is 37.57 degrees, and then that distance for this moment is this whole distance between B and C, which is 90 millimeters plus 170 millimeters. Now all of that equals 0, so we can solve for F1, and we find out that F1 equals 5,207.5 newtons. So that is the force that this bar feels. So that's our F. So what they want is stress. So stress is just normal stress is the force, the internal force over the area over which that force acts perpendicular to the direction it's acting, which will be the cross-sectional area of that bar, which will be, we'll use this diameter, so the area is going to be area equals pi over 4 times the diameter squared, so that equals pi over 4 times 8 millimeters squared, and we get 50.27 millimeters squared. Then we plug that into the equation, we get sigma 1 equals the force we calculated, 5,207.5 newtons, all over the area of 50.27 millimeters squared, and we get that the normal stress in that rod is 103.6, let's do this, it's newtons per millimeter squared, and newtons per millimeter squared equals 103.6 megapascals. So that is our final answer. We know it's a stress. We've done it right because we have a force. Newtons are a force over an area. All right.